Hello and welcome to the segment 2. In this segment, we will look at the training of the language models and how to scale it for the large language models as such. So, while talk about the training of the large language models or any language models for that matter, we will look at also in addition to the training the mixed precision, because mixed precision we have talked about in PyTorch week, and in elaborately we have discussed different data types that are available for AI workloads. In this class, we will not go into deep detail of those data types again, but we will mention what are the data types available and also what type of techniques that we use usually for training such large language models, because in this previous class we have seen the large language model foundations, right. So, we have seen how the next token prediction happens through the layers of transformers, and basically there are several other layers for normalization and probability distribution computation and all these things. So, in this class we will take pre-trained model and try to see exactly how to retrain the entire model first. And obviously, we also talked about in the last class the adaptation, right. So, when we talk about the adaptation, so adaptation means how we take the large language pre-trained model and adapt for a specific domain. So, all the other segments obviously in this week we will see how to optimize the memory throughput and look at the transfer learning approach in large language models, and also we will look at the adaptation, right. So, how to make the fine tuning efficient in the large language model trainings. So, today's focus will be mostly on the precision format revisit and autocast loss scaling and the stability tricks, because here while computing the logit through the softmax or any other activation function, if there are components such as let us say exponential components that we need to compute. So, those times the data type that we use, if they are in reduced precision format, then sometimes what happens is that the data which is the resultant data can get either to 0 or to infinity based on which side of the spectrum the data belongs to, and based on what type of data or what type of mixed precision that we are applying, either the half FP16, BF16 or FP8. So, we have looked at the different precisions of the data in the previous classes. So, we will look at exactly how to stabilize the computations which are involved in the large language models using these different data types. So, the objectives will be mostly to look at the mixed precision, how it improves the throughput and memory footprint as well as the bandwidth utilization. And since we have looked at the distinction between the different data types such as AP32, TF32, the brain float 16, floating point 16 and other precisions, how their dynamic ranges differ from each other, we will just revisit and try to see what makes unstable computation in these large language models and how to fix that. So, basically we will see how to apply stable formulas such as let us say max subtracted softmax or log softmax or log sum exponential. So, these type of functions that we can apply for stable formulations of activation functions, and then obviously we will essentially choose different data type or different data width based on different hardware support that we have. And we will see in this upcoming sessions or segments how these impact the memory footprint, the memory optimization and everything. So, essentially we are bothered about the performance, fitting large amount of the parameters into the GPUs that we have and so on and so forth. So, we all know that if I use single precision full AP32 format, then obviously we will have let us say a large amount of size for the parameter storage. Now if we reduce to floating point, let's say BF16 or AP16, both are 16 points, so it will make it half. However, the data that we are choosing, let's say either BF16 or AP16, that will decide how the performance will go. So obviously tensor cores in the GPUs that we have seen deliver much more matrix multiplication throughput with reduced precision, because we can have large bandwidth for computation, and also the activation storage will take less memory. So activations and temporary tensors will drop let's say from 4 bytes per value to, let's say, 2 bytes per value, and so on and so forth. So it will directly improve the batch size, that let's say 4 batch size I can accommodate with the full precision. At that point of time I can accommodate, let's say, 8 batches per step. So essentially it will improve the gradient calculation in the step. So that will impact the storage, the number of iterations that we go for the training, and so on and so forth. So in the traffic also it will get impacted, because the workloads moving data is often basically expensive, that we have seen, and if we cut down the bandwidth, so the pressure will be less, and here the energy efficiency will also improve. So now the goal is not everything in low precision. We cannot go just full low precision. So exactly where we have to apply what type of precision that we need to see. So let's say the matrix multiplications and convolutions are usually good candidates for low precision. Basically 16 bit floating point will give very good results. However, computations of loss functions will not give you better performance, because you are reducing the dynamic range, and the loss computations will get impacted, for which you are computing the gradient with respect to the weights and biases. So that's why mixed precision is the way to go. Sometimes we will apply full precision, sometimes we will apply half precision, and so on and so forth. It's not entirely the training process. All these steps will be computed with a static data width of either 16 or 32, but it will be a mixed precision training. Okay. So this we have already seen. We have seen FP32 has exponent. So exponent and mantissa bits you are seeing, and if we go from 32 to 16, so we have 16 bits, but based on whether we are using brain float or floating point, we will have the exponents from 8 differing to 5 in floating point. So essentially BF16 will give better dynamic range whether the bits are same. Okay. Okay, so now you can see the typical roles here, and some practical notes for your reference. So the training precision is the key here. So optimizer state sensitive computations and accumulations should happen using full precision, full single precision. We do not go usually the double precision, because that is not required, except some scientific computations that are involved in AI workloads. Usually it is not. And in TensorFloat 32 also it's good for matrix multiplication, because matrix multiplications are fast with TensorFloat 32, because the Ampere architecture and the Hopper architecture and the latest generation GPUs are good for keeping FP32 computations faster. And BF16 also, it will have default mixed precision training on modern GPUs and TPUs. So if you are using TPU or GPU, BF16 is very good in those kind of cases. And if we go for earlier generation of GPUs, AP16 is to go, because we do not have BF16 support before the Ampere series of GPUs. And we have emerging transformer training with the AP8, E4, M3, E4, M2s are also there with 8 bits of precision, and we have exponent bit of 4 and 5 based on what exactly the data type that we are choosing. Usually it needs scaling recipes, because if we cut down the precision, there is high chance that the gradients will vanish very quickly. Okay, so scaling should happen. Okay, so if we reduce the bit size, we have to scale somewhere. Okay, and that's what we will see. So if your stack supports BF16 well, it is usually the first precision to try for training large transformers. That is the prescribed choice, because the dynamic range is always better in brain float, because this data type was particularly curated for AI workloads. The AP16 remains useful because it's very good for loss scaling, overflow checks, and also architecture specific validation, because earlier architecture supports always AP16, and emerging frontiers will like Hopper, Blackwell class GPUs will support AP8 for large transformer training. Okay, so today we will go towards the code section a bit later, but we will just gather few information along the way to see what are the things to expect from the code section, because there we will try to run the codes on a very small GPU with a language model and try to see the full training, and we will basically modify that, or we will expand it and extend it for the adaptation as well as fine tuning in the later sections. Okay, so what mixed actually means inside the training step? So what are the training step? We have the input plus weights. So here we have the model parameters usually remain in default precision outside the autocast context. So autocast is the way to go for mixed precision in the operation level policy. So autocast region, so that means when we go towards the autocast, that means before that we have the inputs, the weights and biases, which are the parameters which stay in the full precision, and then when we enter into the autocast region, which is involving the multiplications, convolutions, which should run in lower precision, this will be chosen automatically by autocast, often in BF16 and AP16 based on whatever it supports, that target GPU supports. And then it will go to the sensitive operations, because if you see the transformers, you have the layer normalization, you have the attention computation, there are multi heads, and then you have the scaling, and then again you have the dot product with the value, so value into attention values, and then you have the logits, and then you have the multi-layer perceptron, and then you have the softmax. So basically the reductions, the normal statistics or softmax or any softmax activation function that you see, or and selected loss will stay in AP32. So these are the sensitive operations which will decide the performance or quality of the training process. So after the sensitive operations you have the backward pass, because the loss computations happen, then we go to the backward pass. Backward pass usually happens with the gradient computation. So gradients will follow the data type introduced by forward operations. So essentially that will be using AP16 or BF16. And then the optimizer step, optimizer typically applies updates in AP32 or another say for accumulator precision. So if you are using the usual optimizer Adam W or Adam weight decay or whatever, so they will use usually the AP32 precision. So you can see at different steps of the training we are using different precision. Okay, so this is the way to go for large language model training, where the tiny transformers will get trained across the GPUs that we have. So autocast is the op level policy and not a blanket cast. You can see we cannot have the autocast wrapped around all the states here. Okay, so we have to have region specification where exactly this autocast should be applied, right? You should not manually call model.half or model.bf16. We should rely on autocast, because that will analyze the codes or the streaming multiprocessors capability based on the kernel that they are launching, and that precision will be applied automatically. So it should be autocasted, and then the backward should be run generally outside the autocast context, because that will run the full precision. And the core idea is basically to give the low precision where the hardware is fast, which is the matrix multiplication convolutions, and higher precision where the math is fragile, which is like the computation of loss function, the activation, and so on and so forth. Okay, so why BF16 is often default? This example we have given before also. here is another example. Here the range example, a value like 1 e power 5 overflows in AP16, but it fits naturally in BF16. So, the overflow and the fitting into BF16, which is getting overflowed in AP16, that we have seen before. So, BF16 keeps the 8-bit exponent of the AP32, that way the dynamic range is wider here. Okay. So, it is the same storage as AP16, however, it will have much wider exponent range. Okay. So, that way it is the default choice for the reduced precision computation. However, sometimes you need to go for AP16. Today we will show that if we go for the earlier series of GPUs, we have no choice. Here is an example of gradient. Here you can see the gradient is about 2 power minus 25, which is about this range. In AP16, this is below the smallest normal value that it can support. So, it will flush to 0 because the underflow is happening here, and in BF16 the dynamic range is far wider. So, the value will be representable in BF16. So, you need to know exactly what is the target system, whether your system is supporting the full range, which is BF16 full dynamic range or not. If not, then you have to have the scaling mechanism applied into your code, otherwise you will get into trouble of getting underflow or overflow of the numbers, either they fall into 0 or infinite or the not a number based on which side it is falling into, and we will see an example in the code section as well. So, for the A Ampere series, Hopper series, Blackwell class hardware, if you have, obviously you should try for BF16 for the first training, and then you can move towards the AP16 only if your budget is preferring to. Okay, otherwise you should stay at BF16 basically. So, now how you should know that in your code whether overflow is happening, underflow is happening, or there are bad reductions that is causing the unstable training. So, while training, if you see inf or nan, which is infinite or the not a number, in the loss or activations, or let us say logits are blowing up before the softmax, these are the symptoms of overflow. So, example is exponentiation of 1000 is not representable in AP16 or AP32. So, naive softmax will overflow immediately. So, it will go to nan. So, typical fix is apply subtract max before softmax. Okay, we will see in the code example how to do that. Or you can prefer the fused attention or log softmax kernels also. And you can choose BF16 instead of AP16 wherever possible. Obviously, this is what I am stressing in each slide, just to be sure whether the BF16 is available or not, that you should check first, okay, whether the target TPU or GPU has the BF16 support. The underflow can happen if your tiny gradients become exact 0. So, it is the other side, right. So, you have the learning stalls. So, learning will saturate. So, because your gradients are becoming 0. So, no learning is happening, no update of weights or parameters are happening due to these vanishing gradients, right. So, these are the exact cases that you see what is happening, and based on that you can actually diagnose whether this underflow or overflow happening. If the underflow is happening, then typical fixes are grad scalar for the FE16 and use again BF16 whenever available. Monitor gradient norms or skipped steps. So, these are the ways to check the symptoms of underflow. For the bad reductions or cancellations, it will have unstable normalizations, the variances and probabilities, it will fluctuate, you can see, and also tiny accuracy drift that compounds to very long training time because of these unstable fluctuations in the variances and probabilities distribution. So, let us say subtracting two close values or summing up many small values in low precision will lose, because basically your meaningful digits will be lost. So, fixes accumulate in AP32. So, that is why this accumulation, the gradients updates should happen in AP32 so that the meaningful values don't get lost in the precision shrinking. You need to keep the layer normalizations or the reductions in higher precision, as I said. So, these are the key or the critical computations in your training pipeline, which should be kept in higher precision. In the smaller networks like CNNs or many other recurrent neural networks, maybe these assumptions will not be applicable for all the models you see. However, for large language models or especially the transformers, these symptoms are visible widely, okay, because you have very large network to feed with. So, in the reductions, this type of typical critical mathematics, we keep the full precision for the overall stability of the program training or the model training. So, here you are seeing softmax done directly, and you see the time where we are applying the softmax, which is the computation with e power xi minus max x. So, this will give you the stability, because now you have -1 0 -2 instead of these blown up values, which will destabilize the computation of softmax. Or you can use the log softmax, as I said. So, this is another preferred way. Instead of the log of softmax, this method log softmax of x is preferable, and then the log sum exponentiation is also applicable wherever you need to stabilize the softmax computations. Okay, the transformer specific save patterns, because here we do scaling, attention scaling after the computation. So, those cases like when we do scale attention scores by 1 by, let us say, square root of d underscore k before softmax. Okay, so we need to do the scaling, use fused attention kernels whenever available based on the target that we have, and keep normalization statistics and important reductions in the full precision. Okay, so always here I am saying full precision, referring to the full single precision, not the full double precision. And obviously AP32 and AP64 are IEEE standard full precisions you can look into. Then when we do the autocast will already be helping with the operations such as, so basically PyTorch sends many operations such as these softmax, log softmax, or cross entropy computation, layer normalization, and summation to float 32 under CUDA autocast, because they are numerically sensitive, they will automatically be sent. And if you are keeping outside of the scope of autocast, then you have to apply the stabilization into the computation. So, if you are writing custom kernels or custom autograd functions, identify which immediate values need more precision based on whether you are going for matrix multiplication, convolution, or other computations. The biggest bugs that you will usually get into is when you are using fused paths, which will drop the reduction into the low precision automatically, and that will get into problem. So, here is one such low scaling methodology usually we use when we do compute or do train in AP16, because earlier GPU machines which are earlier than the Ampere series, so they support only AP16. So, we compute the loss. Okay, so forward pass runs the under the autocast, compute the loss L, multiply the loss by scale. So, tiny gradients we make them large before the backward computation. So, that way gradients are computed in the scaled domain. Okay. And then we need to undo the scaling. So, we do the gradient unscaling, thus the undo of scaling before the clipping or optimizer update, which is the step function, or let us say skip. If there is the overflow appearing, then we skip the step and we reduce the S, which is the scaling factor, which will not blow up the gradient beyond the range it can tolerate. Okay. So, Here is the one such concrete example. Here we have a gradient which is 2 power minus 25. In AP16 that is too small and it may flush to 0, and we scale the loss by 2 power 10. This is one such scaling mechanism that will give the gradient or take the gradient from 2 power to minus 25 to minus 15 during the backward, and this is much easier to represent after the in this backward scaling, and after unscaling we recover the unintended or intended update magnitude based on how much scaling that is done before. Okay, so in this code section we will see how to autocast. So amp.autocast that will be applied in the code section we will see. Okay, and we have already talked about what are the things to avoid, and here some nuances for LLM specific training. So attention scores can explode because you do the QK power T computation which combines many products. So you have 1024 by 1024 matrices multiplying each other. So essentially each values are multiplied with many, and then the many products will get accumulated. So with long contexts or sharp activations, logits can grow larger before softmax. This is why scaling and fused kernels matter. So if you are in domain of, let's say, convolutional neural networks, it may not be applicable, but in the LLM domain this is applicable to do the scaling and fused kernels application before the softmax. Linear normalization need careful statistics, means, variance or RMS computations like. So these are the computations which can lose accuracy if all intermediate reductions stay in low precision. Okay, so we need to take care of them, and also long sequences amplify error because more time steps means more reductions and more attention work. So more opportunities for small roundings effects which will accumulate, and it will amplify the error that can happen. So the policies are linear, the QKB computation which is the QK power T into V. So this is the QKB computation, and then the MLP general matrix multiplications. These are in this range, okay, usually done. Attentions, softmax and log probabilities often done in full precision. Normalization statistics also done in the AP32, and optimizer is also done usually in AP32, and final output tensor downcast if it is safe, that also we can check. Okay. So with this we will see the code section to understand what exactly is going on in the training of large language models as such. So in this we have installed the transformers. So these are the packages that we will try to use, and from the transformer package we have imported these are the packages which has auto tokenizer, the model for causal LM, the causal language model that we will use today for training, which is a very tiny language model for demonstration purpose. So if you want to run in GPU, you can change the runtime to GPU. So if it is in T4 GPU, you can select the T4 GPU. If you have the access to Hopper GPUs or other GPUs, also you can select. Okay. So today I will show one GPU which is T4 GPU freely available, so that all of you can try, and I will show exactly how to go into the other GPUs also. Okay. And this is the TPU. So if you want to go for the TPU execution, that also you can select, and another TPU which is a high end TPU which is not freely available, that is also there to select. Okay. So the change runtime will select the device for which we are running the applications. So I will not run the all the cells, but try to show you what exactly is going on here. So here first obviously we have the installation and importing of all the packages, and in this code section we are trying to see what are the GPU available and the GPU name. So essentially the capability of the GPU. So these device that we have CUDA Tesla T4, So these are the devices that we can see it here, and then we can actually see whether this has the support for AP16 or support for BF float or BF float 16 or not. This check is happening here. So you can run this function to choose. So basically it's checking the capability. So from this device capability, we are just trying to see if there is a support for the exponent support for greater than equal to 8 bits or not. So this is floating point BF float 16, or otherwise if you do not have support, we will use floating point 16, right. Okay, so the device is set. You can see the device, and now if you run this, you can see that we have the support for float 16. We do not have support for BF 16 in this T4. If you have chosen the H100, which is Hopper series, obviously you could have seen here BF 16 support is there already. Okay. Okay, so in this code section, you can see that this is the naive softmax computation, which is the exponentiation, so e power x divided by this computation, and stable softmax, which is doing z computation, which is x minus x max, and then this is applied into the exponent. Okay, so this way the computation will stay stable. So if you see here, the naive softmax tensors, you can see this is blowing up. So basically we are having NaN everywhere, because we are computing the softmax of these values, and if we go for the stable softmax computation, we are getting the stable values here. Okay, and this is the difference between the torch.softmax. So if you are using torch.softmax, this is also actually doing the stable softmax computation. Okay. So this is the computation, or if you are using naive softmax, this is this will actually reduce the stability. Next, we will try to build the tiny instruction data set for the language model that we are going to fine tune. Okay. So here we are will apply tokenization, then we will extract the labels for causal LLM or causal language model. So causal language models are basically language models like GPT like models, which is trained to predict the next token given a context or set of tokens. So it will look at the previous set of tokens, and basically it will predict the next. So based on the context, it will predict the next set of tokens each iteration. Okay, so here is the data set that we have. So we have few questions and answers. So this is the question, and this is the answer, question, answer, and so on and so forth. So this is how the entire data set is formed, right? And for giving the questions and answer pairs, we need a format. So this is the specific format in the format that we give to the LLM to learn. So essentially the format is instruction, what is the instruction, and what is should be the response for that instruction. Now if we build the demo text, which is the this data set which we will train with, and we just print the first text. So essentially this is the instruction, explain mixed precision training in one paragraph, and here is the response here. Okay, so the dataset preparation is done, and then we are actually creating the or importing the model here. The model name is Distal GPT-2. So this is a very tiny causal LM, and we have the maximum length of context here 128. The batch size is 4. Gradient accumulation steps are 4. So that means we are saying that you do not compute gradient for each batch, rather you wait for 4 steps. Here 4 is the gradient accumulation steps. So this will reduce the memory requirement. This is one trick. So these are the few tricks that we will see all along the way. And maximum updates, 30 maximum updates will happen for the parameters, and this is the learning rate. And while setting the or importing the model, it will actually try to see what is the tokenizer configuration. So basically it will download the vocabulary which is used for tokenization of this model, and essentially the relevant auxiliary documents will also get downloaded. Okay. And here is the definition of tiny instruction data set. So, where we are initializing the data set and then seeing how many samples are there and each length and get item. This you have already seen in the PyTorch training. And then the data class. So, this is the causal collator which will collate the information for the so it will actually see each sample, it will see the text, and from that text it will tokenize, and after the tokenization it will extract the IDs as labels, and if there is padding happening. So, basically this causal LLM or the causal large language model or this causal language model expects fixed length of context. So, if there is shorter sentence it will pad. So, that is why this padding equal to true was there while tokenization, and if the padding is there, so it will skip that. So, basically this is the it is a trick to say that if there is a padding you just skip for those trainings. Then the we are returning the encoding the value. So, basically this is the raw text to tokenization vector happening, and this vector is getting returned, and then the data set, collator and loader is there. So, data set is the warehouse, the collator is basically the packaging happening, and then the loader, you know, the conveyor belt or the data loader, which is giving the data to the training with the batch size that we have defined, and so on and so forth. So, this is how the input has been configured. Now, here we are seeing this particular model, right. So, this is the prompt that we will give, explain mixed precision training in one paragraph. This is the instruction that I will give as instruction, and I should expect some response. So, this is the prompt. So, this is the format that you remember, and in this format this language model should start writing from here. So, this is the instruction that I am giving, and the generated text is essentially doing this exactly, and the decoding is happening, and then the tokenizer decoder will decode what exactly is given as output from the language model and what that means in terms of actual token from the vocabulary that we have downloaded. So, here is the base model and here is the tokenizer, and basically I am printing. So, now we have not done any training. So, we just downloaded the model, and you can see that the model shaped tensors are getting loaded. Then the weight loading happened, and basically the GPT-2 language model head model. So, this is the structure of this model, and you can see that the baseline untrained model is taking this instruction and giving this output as response, right. So, your response is figured out by this generated text. Since this is not trained, we do not get any value. Obviously, I mean we have not trained with the data that we have created here, right, here, right. So, this is the data set that we have created. So, now in this train model we can actually see exactly where this mixed precision is applied. Now, this is the model, this is the loader, use AMP is equal to true, and this will activate the AMP autocast in this subsequent configuration. So, here is the model definition which is transferring the model to device, and then the train is called, the optimizer is defined, total updates was 30 as I defined before, warm up steps, you can see how the learning rate will go, right, and then the scheduler, the scaler. Okay, so, this is the grad scaler that is applied, and then we have the history to list down or to keep track of what exactly happened in this training process. Update step is 0, micro step is 0, start is so to track of time, and then if the CUDA is available, it will reset to peak memory, and then it will reset the gradients to 0, and then the updates will happen. If the updates is less than max update, then only it will go for the batch, and for each batch it will actually see, and then we are creating this context under which context this training will happen. You can see that torch.autocast is happening with this device that we have defined here, and if we are using the CUDA, then otherwise it will have null context. So, with this context we are forward passing with the output and the model, then the loss computation is happening with the gradient accumulation step, and then the scaler is enabled, and then the so basically if the scaler is enabled, then it will do the scaling and then the backward computation, otherwise it will directly go towards loss dot backward. And then if the gradient accumulation step is less than equal to your micro step, so that is the 4 that you have defined. So for each 4 steps, so batch update, gradient update will not happen. For each 4 such batches passed, then only it will actually do the update, and basically that time we need to do the unscaling. So this is the optimizer step. Here we are doing the step which is the gradient for the optimizer step function, and then the scheduler is called here, and then the 0 grad is called here again to reset the optimizer. Okay. So this is the record that we have had: update, loss, LR, gradient and scale value. Okay. So you can see the scope that we have defined for autocast, which is basically this context under which whatever we will see, it will see the autocast. So that means it will automatically decide which precision it will fall into in this computation. So if we run this entire flow, you will see that these functions have been defined, and we will call this model from the pre-trained to device, and basically we will train the model in this particular block. Okay. And update 1, update 5, update 10, update 20, 25, 30. So 30 updates happened, and you can see that this is the peak global memory allocated, which is in size of GB. Now if we print with generate text the for the model AMP and the prompt with the prompt, we will see exactly the definition of mixed precision training which we have trained with. Okay. We can see the inspection of the entire history, so how the loss has evolved to 0, almost towards 0, and the complete graph with loss and update step we can see here. So this is how the full training of the language model that we have just seen, defining within the scope of autocast, and obviously applying the scaling, graded scaler, or the safe or stabilized computation wherever required. Okay. So with this we will conclude this segment. So you should try to play with the segment for training that we have discussed, and try to see exactly which are the stages which will be required for your case. Okay. So in the upcoming segments we will see in detail the exact way to optimize the memory, okay, and also scale it for the any GPUs that you have. Okay. Also the distributed computing in the LLM kind of domain that we will see, and we will also discuss fine tuning and adaptation. Thank you.